interested in many cases. And in this case, in this environment, the things or areas which are of interest, when we have a project going on, are first of all in interested in middleware. We do a lot of work on software components that will support some of these applications on the infrastructure middleware. So this is server middleware that we work on. And I'm going to give you an example of one of these projects that we're doing. The other area is looking at the client-side software. What are the pieces, the components that you want to develop on the client side, which drives things, drives a certain platform independence, so that you can actually have application components that can be sort of enabled or accessed through multiple devices. So you don't want to we don't necessarily want to focus on a single application, single device environment, but want to be able to cover a variety of devices. The third area that we look at is user experience, which is a very important and major issue that we spend a lot of time thinking about, right? Which is, especially when the portal or the access method to these services and applications is on little devices. And you have, in many cases, limited interaction capability on these devices, right? So you have small little screens, small keyboards. Sometimes you have just a stylus interface. Sometimes you have only 9 keys, which you go like this. You know, it's now a very curious phenomenon that happens almost all over the world, except in the U.S. that I've not seen too much, which is that people sitting in buses and trains only like look at their cell phones and go like this, because they are sending chat messages back and forth, which is the widest used wireless application ever in the world. But that user interface is extremely cumbersome to use, right? What you want is a interface that will give you a much richer user experience, something that will give you more efficient access to this information. So a significant part of the research effort goes into improving the user experience through things like conversational interfaces, not controversial, through things like multimodal, in other words, mixing graphical and voice interfaces together so that you can get some very efficient interaction methods possible. And through things like overall improving the efficiency. If you look at environments like multiple devices that you may have that you can use cooperatively together, right? And the last but not least area that we look at is application development tools for these environments, right? So in many cases, a lot of times you build a lot of infrastructure, but one important thing that you have to give a lot of attention to is how easy or how difficult is it to build applications for this environment, right? If it ends up that the environment is is very rich and nice, however, to build and deploy an application and to maintain that application takes several person years of effort, then that infrastructure will not get used that much, because the cost of building and maintaining an application, if you look at it today, the people cost involved oftentimes overshadows the investment or the amount of money that is required to deploy a certain level of infrastructure, right? Machines are getting cheaper every day. Infrastructure is getting cheaper every day. There's unlit fiber bandwidth of several million gigabytes or whatever it is available. However, skilled people who can develop applications are still in limited supply, right? So in order to improve the overall efficiency or to reduce the cost of developing these applications, you need to have very efficient application development tools, right? So that sort of is a overall high-level view of the kind of areas that we are looking at. I'm going to give you, I'm going to take some examples from each of these and go into a little bit of detail on one example project from each of these areas, right? Any questions at this point? Okay, so So what I'm going to do is give you a example of a project that is looking at some context-aware application and some infrastructure middleware that we are building for that. Another project which is looking at wearable computing. We are experimenting with certain small form factor computing devices. I'll touch upon application development tools and then open up and we'll have some discussion. Okay. So let's look at the. I talked about this already. Let me skip this one. So let's look at what a context-aware application is. Right. I mean, this is many of you probably already know all this, so this should be fairly obvious to you. Context you can think of as sort of a generalization of things like location awareness. Right. So context includes things like location. Things like what are the things that I have in my possession, what is the current state, what is my objective, all these things, right? And so if you look at you may have heard or thought about, in fact, of several different scenarios like this, right? The shopper. So there are certain geographical locations that have been demarcated or differentiated. And there's a shopper is coming around and has a shopping list at the current time that he or she is interested in picking up. And there are different businesses that are broadcasting, what are the current offers, which may in fact be changing depending on the time of the day. If it is middle of the afternoon in hot weather in New Delhi, you may want to want to advertise that you have cold soda available, but in the middle of the night in Salt Lake City, you may want to have something completely different advertised, right? So different businesses may be broadcasting offers for different things. And a shopper may be driving around in this locality with a certain shopping list, and you can have a matchmaking algorithm which looks at the location as well as the shopping list and push certain information to the shopper. And if the shopper actually ends up in a different location, so here, for instance, there may be a match between you're looking for aspirin because the traffic is giving you a headache, you might get something there. And if you get to the downtown location and the drive is becoming boring, you may want to pick up bubblegum and clarinet. And so these kind of matchmaking applications and scenarios we've thought about and have discussed this in many cases. So this is nothing new. But you don't see too many of these applications still, right? So the scenario is nothing new. So we've talked about this, I don't know, for several years, 4 or 5 years at least. Right? And there are certain information sources that are slowly becoming available also. So the infrastructure is slowly coming into position, right? Which is there are cars which have some GPS navigation systems, so you can find out the location of a car as it's just driving around. There is some areas have real-time traffic information, e-business data you can access through some web services interfaces, not very widely used yet, but available still. However, you still have you don't see too many of these applications deployed, right? And there are our contention, of course, is that, and this goes back to my previous point about how easy or difficult it is to develop these applications. So one of the things that we claim is essentially that there isn't a easy enough environment to author applications and to execute them efficiently. So you need to have a good programming model or a good application development paradigm that you can use to develop these kind of applications. And you need to have a very efficient runtime, which will, or an execution environment which will support these kind of applications. Right? So the key technical challenges in these kind of applications is essentially the nature of the application, which is you need to combine and mediate among the multiple sources of data. There is location data coming from the vehicle. It may be coming from a GPS receiver, or it may be coming from a cellular phone through triangulation and whatnot. There is information coming from the web sources, which may be traffic information, may be web services broadcast by different enterprises in the location, and what have you, right? And the nature of the data and the data sources will differ. So there is a heterogeneity in the kind of protocols that are used. Some of these data sources are push type of data sources. You go request the data and you get it. Some of the sources are the other way around. Some are push sources where there is a constant stream of things coming at you, and you need to filter them and get the right one. An important another consideration is to protect privacy and provide a secure environment where you can actually provide enough of a guarantee of privacy so that your location information is not broadcast or given out to anybody who requests it. And you need to have certain guarantees on the quality of the information. Is your location information half an hour stale, or is it within the few minutes or a couple of minutes that you're able to get that information? And a lot of these times the inherent environment is sort of distributed. You have different administrative domains that you have to cross in order to get a lot of this information. So one of the pieces of work that we're doing is to build some infrastructure. So both the runtime environment as well as a application development environment, which allows you to mask some of the complexity of this data sources from the pervasive data sources using the execution environment to some extent, right? So the computation model that we're following here essentially is you have a hierarchy of composers. So external data sources. So there is a registration protocol, you assume that exists, which is something that we are developing as well. So that an external data source can actually register themselves to this runtime. So the registration would include things like what is the type of data, what are the guarantees that the data source can actually provide on this data, and how do you gain access to that data, what are the information that you need to send to get the data, the required data back. And the runtime system essentially from the application layer masks the complexity of these data sources, right? So in the application, you would just have data composition statements, which says things like I'm going to the location of Manish at 11 a.m. today with the guarantee of 5 minutes of currency in the information, right? And the composer's job essentially is to take that query information, essentially decompose it into the component queries that may then be serviced by other composers or directly by the data source, external data source. Right? And so the system would essentially bind the composers to the right data sources. And if some data source, the idea is that if a particular data source actually disappears, let's say that suddenly my cell phone coverage actually goes away, you could sort of gracefully fall back onto another source which may have not the right level of guarantee. For instance, the GPS receiver may have location information which is 10 minutes delayed or 5 minutes delayed versus the 1 minute delay in the cellular phone data. However, you have enough of an information so that applications which don't require that level of precision can still carry on with that source of information, right? So the runtime system essentially gives you a certain level of masking, so the application development becomes easier. And in addition, one of the objectives of the runtime system essentially is to make sure that this can be distributed and you have a certain level of efficiency in the deployment, so that you can have a higher level of scalability on an infrastructure like this. Yeah.
How do you find those graphs of composers?
How do you do?
How do you define those graphs?
So there is a programming, there's a composition language that we have, which we've developed essentially, which is essentially a declarative syntax for defining how the composers have to put together, right? And in the runtime, essentially, the runtime system takes care of taking that specification of the composition and then breaking it down using the registered information internally. So for instance, if you had a request for a location with a certain position, you may, let's say the temperature at a particular location, you may have a composer which gives you, or a data source which gives you temperature in centigrade scale, and you may have a composer which takes the centigrade scale information and converts it into Fahrenheit. And the top-level composition essentially can break the request for a Fahrenheit temperature in a particular location down into request to the data source, and then the next composer which will then combine the two things to get the Fahrenheit temperature information.
Whose responsibility would it be to build and combine that? Is that the responsibility of the application program?
So there are two things. The application, so there are two types of developers that you can, or two roles that you can see. One is a developer who is only interested in writing an application which makes use of this context information, right? And they don't worry about exactly how the composers are lined up and things like that. They may be able to take advantage of an existing inventory of composers which have already been defined. Or there can be another role, which is essentially a set of people who develop different composers. Right? So you're right in that ahead of time you will not have a complete inventory of composers that you can rely on, but the process is essentially to go have an ability to develop additional composers as well.
So in this case, you assume that the application know a priori what is the aim or the objective of the composition. What if that aim or objective change with time? So in the morning you need something, in the afternoon some minor modifications of service.
If you have a fixed composer, of course, so the time difference, can maybe one way it would get handled is the data source itself may be able to mask that or provide it, the time varying information, so that the composer does not have to worry about it. And second, another way to do this, of course, is to have multiple composers which you can that you can call from the application level, depending upon exactly what your objective is. Is it in the morning you want temperature in centigrade, in the evening you want temperature in Fahrenheit, whatever, right?
So if you have these services, data sources which are already registered, and you have sort of the dependencies with your composers. So intuitively, why doesn't it make sense to sort of make out the abstract graph and depending on the request at a particular instance of time, give that information rather than waiting for the application interface to give a objective and then to compose it?
There are pros and cons to both of these, right? If you do a dynamic composition, you have a greater flexibility in being able to take into account changes in the data source availability, right? On the other hand, if you have, you can drive greater efficiency or faster execution, for instance, if you had a static binding already. The main thing that we are trying to avoid is not to have a static binding to a certain set of data sources, right? You could have the composition graphs defined ahead of time, but at a certain level, you want to disconnect essentially the binding of that composition to this particular data source, because you don't want. So it's precisely like this. So if you take a different scenario, like you have data sources in a vehicle that is looking at all different types of engine performance and speed and whatnot. Certain parts of this sensors or the data sources may actually fail at some point, and you don't want to have the entire application failing. You want a graceful degradation where you can switch over to a different binding to the data source.
Also a question, in your system, do you have a way to migrate the composer to other devices, like on the sensor itself, for example, which would cut down the communication requirement in certain cases?
So the intention is that in the runtime system, above this, would all run in some infrastructure, server-side middleware, right? And the efficiencies are derived essentially by being able to distribute these pieces across multiple servers. On the device end, where the data sources are concerned, it is the data source end which would then migrate, and you could in fact have multiple devices providing you data.
Right. So in your model, the idea is the data source is viewed as relatively passive type interface, and then you do the deep binding or
exactly
other things on the server.
That's right. So the runtime environment, I mentioned this already a little bit, which is there is a component which takes in queries and finds the right data source to bind to, and then returns you the data. So the specification of the query comes in only with the specification of what kind of data you want, what are the guarantees that you want on this data and whatnot. And then the input broker element just passes you back the right level of data coming back. The composition engine essentially takes in essentially the specification of what is the kind of composed information that you're looking for. So this is data coming in, going back up this you can say information that you're interested in, right? And there is, as I said before, there may be a library of composed specifications available, which are built ahead of time or could be built by the application developer. And the composition graph itself may be specified through some syntax. It could be a Java syntax or some other declarative syntax. And we have a declarative syntax that we have written about as well. I won't go into the detail of that syntax, but some of the examples. So we've actually used this system to build some sample applications. One sample application that we built specifically is would have actually helped me this morning, which is a dynamic route planning information, which given a starting point and a destination, and you're dynamically changing location information, as well as other traffic conditions that may be changing on the road, you could get a different route plan. And this is something that we worked with Ford Research and demonstrated last year at a automotive industry conference. This just shows the simulation screen because we wanted to have a convenient way to simulate traffic conditions, because you cannot call up an accident on the George Washington Bridge. You wouldn't be viewed very kindly if you do that. So what we wanted to do was to have an interface which actually you can drag and drop onto. So the map data is real. The location data can be real in this thing, but you can then drag and drop different conditions on the road, like hazards and weather conditions and accidents and whatnot, and have the route plan essentially be rerouted dynamically. Right? So there are some sample applications like this. You can think of a whole range of different scenarios where this kind of infrastructure would be useful. Large telematics type of applications are one where you have, let's say, large fleets where it could be automotive, trucking fleets, could be taxis in New York City and whatnot. So there's a large number of mobile assets that you're trying to manage. And you want certain infrastructure that you can use to easily change and program the application. So that today I may be looking at what are all the cars that are available, south of 56th Street in Manhattan, but you may want to find out something else, and you can easily program some application like that given an infrastructure like this. Right? So that's the objective or something like that.
Does this application have both pull and push modes, or is it relying on push?
That particular sample application had a push model, I believe, for the traffic incident, and a pull model for the location.
Do you have any?
But this is, of course, I'm sorry. So this is just a simulation, right? So this is not a actually live deployed application.
the type of data that these composers exchange? Do you have any constraints on the data, either XML or?
Yeah, of course. So the data, we have defined a schema for how the data should be. First of all, for the source to register with the runtime system, and then to provide the data. Right. So it's an XML based syntax. Yeah.
You're describing something, for example, shopping examples. It's sort of a database technical problem. It's actually a very psychological process. Do you include that in your work to actually think about how people make such decisions?
Short answer, no. But we should, I think, because there may be interesting technical implications on some of on some of those things like that. That if the response time is if I don't get a coupon in 30 seconds, then I will forget about this particular store and move on to the next store and what have you. So there are interesting technical implications on psychological phenomena like that, of course, but we ourselves have limited skills in that area to really use that kind of information, or at least we have not looked at it yet.
I'm thinking of something as simple as response time, because I need a shirt, but I don't buy a shirt in any store that happens to have a shirt.
Sure.
It's very specific background knowledge that guides the kind of thing I'm willing to do. And even things like route planning.
Yeah.
I mean, it's a private process and it's more complex than just knowing where traffic is. And obviously you want real applications that people will buy.
So in many cases, so things like in the retail scenario, right? We in many cases rely on feedback or information from some of our partners and customers in order to figure out how that should be reflected in the technology, right? So we are not in the business of selling shirts, right? Sears is or Lansdowne is, and they have a lot of domain knowledge. They know precisely what kind of shopper comes into their website or walks into the store, and what sort of display of their shirts will actually persuade somebody to buy. Right? What we want to do is not to essentially replicate or to try and reinvent the things that they know about, but to actually learn from them and see what are the pieces that actually can be reflected into the technology, which will improve some of the technology infrastructure to take care of these kind of things, right? So, but those are just words. In practice, we've in this particular effort, we've not done that yet. Right? But definitely, I acknowledge the fact that this is important. Right?
So my question is along the line of the data. The amount of data somehow your structure can process it. So basically, the typical for the project, if your data is the size is too small, you cannot differentiate those things, correct? And if you want to differentiate it, maybe you want more data set. Then do you have somehow the rough calculations of how much data you need, so much processing power to actually done that using your structure?
So I'm trying to let me understand your question.
So it's not really related to XML, so some kind of input but also just for your structure. So how much you can handle based on how much computation power in that sense?
I don't have a number off the top of my head. We have done some work in looking at what are the scalability and efficiency issues in deploying an infrastructure like that. But I don't have the concrete numbers off the top of my head. Okay, anything else? Any other questions? So I'm going to move on to so we looked at one sample project which looks at the sort of infrastructure middleware. Looking at it now at the other end, which is on the device end. So a lot of these applications you want to be able to access from interesting and rich device environments, right, or device classes that can then hook into this infrastructure and be sort of the small window that you use to access this information and the services that are available in this large infrastructure in the back end. And One example project that we did essentially to study both the usability of some of these devices like this, and also to sort of be like climbing Mount Everest, which is just to be able to show that you can actually do it, climb without actually using oxygen or what have you. We actually built a full Linux level machine on a wristwatch form factor. So some of you might have seen this before. The latest incarnation, which is version 1.5 of this hardware, and unfortunately I couldn't bring a sample today, but this is a representative, not the life size, but representative picture of the watch. And on the hardware side, some of the facilities it has, this is a 320 by 240 LCD display, and it is a touch screen on top of that, so that you can use it to design pull-down menus and whatnot. There is a roller wheel down here, which you can use to move through menu items which show up on the screen, and go and click on it to pick one of the menu items. There's a fingerprint sensor out here, so you swipe your thumb through that fingerprint sensor, and it takes a bitmap image of the fingerprint, which you can later use either to process internally on this processor here to match it against some fingerprint, or you can send it over to a server on a wireless connection to have it processed on the server. The wireless connection is provided by a Bluetooth wireless, which is integrated into the watch. And there's also an IRDA connection for if you wanted to just use the standard infrared connections. These are charging pins over here. There's a speaker and microphone connection in here so that you can connect an external speaker. So you can use an audio, you can use the audio channel through this external speaker and microphone. You can also use an audio through the Bluetooth connection here. So the Bluetooth standard specifies an audio input output as well. And the processor is on it. There are two versions that we have developed. One which has an ARM7 processor and with about 8 megabytes of DRAM and 16 flash. We also have a PowerPC version, of course, which with the same capabilities as well. Right. So those are the and there's a cradle which comes with it, which you can put it on the cradle to charge overnight. The battery lasts. If you don't do anything with it, which is essentially to just display the time, battery lasts about 36 hours. If you do, and I'll have a few things to say about the power consumption. That's the hardware. On the software, it runs 2418 version Linux, and Bluedocker is the Bluetooth stack that originated in Watson. Has the XLM Windows interface on it. We've changed the Linux kernel, worked with the Linux kernel to essentially get a low power version. I'll tell you a little bit about what we did there. There are some sample applications that we've developed on this, some personal information management, calendar, and sort of alerts and things like that on it. You can obviously interact with other devices through using the Bluetooth connection. It has an accelerometer. The other thing that I forgot to mention inside in the hardware side is that there is an accelerometer, so that if you move your hand over, you can actually sense the direction and the distance that you have moved, so that you can have neat little applications like when you point on the screen, you can have the mouse control following the point, the place we are pointing at. We've done wireless user notification and using the fingerprint sensor, use it as a security token and things like that. An interesting demo that we built was of a mobile IPv6 demo, where you can take the watch from one access point with a particular IP address, go to another one, get a different dynamic IP address destination there, and have application data rerouted, which is a standard facilities in IPv6, which you need to enter there. So some few words about what are the interesting things? So very often in this kind of talks I get asked the question, why did you build the watch? Really, is IBM going to be in the business of selling wristwatches? And the answer is no. The answer is essentially the research project which is aimed at building something like this is essentially to look at what are the constraints imposed on an end user when you have a device like this. What are the facilities or the opportunities that you have to access and have rich applications delivered to this kind of device when you have a rich software infrastructure like a full Linux operating system stack on it, right? And what are some of the interesting peripheral devices that you need to have to interact with some interesting applications, right? So that was the main objective for building a watch like this. It may end up eventually that somebody will manufacture and sell it. The watch itself was actually, that form factor was developed with Citizen Watch Company research side also. Now, and another important issue that you get to address when you're developing a device like this is what are the power management issues. For instance, the typical today in many cases most people have actually become sort of been familiarized and have accepted the fact that you use a cell phone and you charge it overnight at the end of the day or at night, right? This is a very standard usage model that most people have sort of accepted. So you want to get a computing device also which has a similar sort of battery usage pattern, which is you want to be able to use make use of a lot of interesting applications and usable things over the course of a day, and maybe overnight you want to charge it. In order to do that, given the small size of the device, you want to actually look at power management very carefully on a device like this, right? And the power management, some of the factors which influence power management are what is the usage scenarios that you would use this device for. If you constantly use it, then and it is running very high-end applications, then the power will drain very quickly, of course. But typical usage scenario for a device like this, which is maybe a PDA type of style of usage, is that you would use it for a little while and then it would go down into a sleep mode, and you would wake it up after a little while and use it some more. Right? The selection of the hardware components obviously has a lot to do with how fast or slowly you drain the battery. What sort of drivers are used at the operating system level, what is the software level that you're using, and the kind of application level things, user interface is something which requires you to wake up the screen and have very rich graphics on the screen will drain the battery quickly, of course. And if you look at the duty factor or the usage, relative usage scenario, so this is what I said, if you don't use the device much, the relative battery life is very high. So this on the x-axis here is the duty factor, which means essentially given a total amount of time, for what period of time there's actually the fraction of time there's actually the device is active or being used. So there's nothing really earth-shaking here. It's fairly intuitive in the sense that if you over a certain period of time, if you actively use a device, the battery use life is much lower. The relative, again, even within the time of active time, if you can put the device to sleep for short chunks of time and wake it up, even within that sort of usage pattern, you can drive up the power. So if this ratio, which is the active time versus the sleep time, is lower, then you get higher battery usage or lower battery drain, right? So the interesting statements to make out of this is that if the device is being used heavily, right, which is that the duty factor is high, then you want to focus on techniques which will actually lower the active power usage. So when the device is actually being active, and how much power the CPU is going to drain, how much power the different device drivers are going to drain, you need to focus very heavily on that. If it is being used sparingly, which is that this duty factor is low, in order to extend the battery life, the more important thing to look at is in the sleep mode, how much battery is being drained, right? And as I already mentioned before, statement down here essentially is that people, care about how frequently you have to end up charging the device. In many cases, it doesn't matter how long you have to keep something on recharge in order to get it charged. So one thing that we did was to actually work with the Linux kernel essentially to change the timer, essentially the timing scheme in the Linux kernel, so that you don't have these frequent timer interrupts for which you have to wake up and look at whether there is any activity to be serviced. Rather, if there is a idle time, you put the processor to sleep and wake up only when there is an interrupt coming in from the external. You put the processor in standby and wake up only if there is an interrupt coming from outside, or at some longer periodic length you wake up and look for work to do. Right? So there's this actually improves the idle or standby power usage, so that if the watch is not being used very heavily and it is only displaying time, you actually can save a lot more power. Essentially, you lower. I don't know whether you can see it, maybe below the table then, but you can lower the flow of power in the idle state from here to down to here by putting it into standby or deep sleep mode. How much time do I have? 5 minutes? Okay, so let me just discuss a little bit about application of open tools, and then maybe a couple of pages, and I will stop, and then we can have some discussion. Right? So, as I mentioned in the beginning, one important consideration that you should one needs to have in many of these pervasive computing applications is how easy or difficult it is going to be to actually develop applications for this. Right? There's nothing like having a million developers, to be writing programs into your infrastructure, or to writing applications which are enabling wireless access to data. Right? However, we are not quite there yet. I was talking to a friend of mine who used to work for this startup company. Used to work for the startup company is a very common phrase you hear these days. And they were in the business of essentially delivering information, very valuable information to Palm Pilot devices, right? And they switched from a Palm Pilot to an iPad, or not switched, but they wanted to add access from an iPad, pocket PC device also. And essentially, they had to rewrite that entire application. The application, which took them 3-4 months to develop, had to be replicated essentially overall again to retarget and deploy onto another device, right? And that is a cost that in many cases a lot of people are not willing to or able to bear. But at the same time, you have devices coming online. Essentially, Nokia releases 2 phones every 3 months. Motorola releases in competition another 3 phones every 2 months, and so on. So there's pretty much one device or one new device coming, which has wireless data access, has a user interface, which in some cases has a color screen, has cameras, has a keyboard, and all these things. So there's one new device coming pretty much every week, right? Now, if you're an application provider or a service provider who is targeting people having these different mobile devices, you simply cannot afford to cover all of these devices, right? Because the cost of developing and deploying these kind of applications on 50 different devices, which have some of this little screens, some are black and white, some are color. This variety is just very too difficult to try and cover, right? So we are looking at what kind of technological support you can provide in order to improve the deployment or the development and deployment of these kind of applications, right? So one project that we mentioned is to support application development paradigm which will support multiple devices. So let me skip this and go to this one, which is easier to explain. So of course we're looking at applications which are web-enabled applications, right? So there's they assume that there is an infrastructure which is delivering some web data onto some devices. Right? In a traditional case, you have a standard browser, let's say, which is accessing this information, and in a typical model view controller paradigm that is used to design these applications, you get a request coming in. There's an action handler which looks at what kind of button was pressed or what action was actually initiated, which dispatches the right connections to some backend. Typically in a J2 Java model, J2EE model, there's a set of Java beans which give you connections to some backend database, right? And the answer would come back, and you have some Java server pages typically which generate the next page that is to be delivered back to the browser, right? Now, in the if you wanted to then deploy the same application onto a wireless device, onto the small screen, in many cases what you had to do was to replicate this entire infrastructure over for that device, so that the action handlers will end up being different. The Java server pages, which actually will generate the output markup, which is could be WML or compact HTML and what have you, would be different. In many cases, you can share the model part over here because the backend connection can be common among multiple access methods. So that commonality comes already. But the significant part of the application development, as anybody who has written a large application will know, is in the management of the user interface. Right? It's much easier to actually just write the backend connectors and very quickly get data from a table, but to lay out the user interface, worry about where to put the buttons, making it look nice, making all the actions, the button pushes be handled appropriately. All of these things is what takes a lot more effort. So this is a lot of the effort is actually in these pieces, right? And if you wanted to then deploy also to other devices which are not known early on, then it becomes even more complicated, right? So the approach that we are taking essentially is to have an authoring tool which will allow you to describe or to develop a very generic model of the application, and specifically we're not worrying about this part, but specifically the action handlers and the view or the display of the information onto the screen and the user interface part. Have a generic model-based paradigm which will allow you to develop the application in a generic fashion. And then you have two choices. The developer can actually deploy at design time a new version of the application by just using some automatic methods that are available in the tool. You can look at it and check out whether this part of the application actually looks okay or not, and make refinements or make improvements on the look and feel of the interface. Or you can choose also to deploy a generic version of the application, which is then translated at runtime to deploy to devices which may not be known at design. Right? So essentially the paradigm is to provide as much of support to the developer as possible without taking away the freedom of changing the application's look and feel onto a new device if that change is necessary. Right? And so ignore this part for a minute. The design paradigm that you or the methodology that you would run through is essentially to design a generic controller and view elements for the application. You may develop the Java beans or the model part of it along with it also if this is a new application And then, as I said, you may have coming out of it a generic deployment of the application, which is then used at runtime to adapt and deliver to a particular device. Or you may go through a specialization step. And in the specialization step, essentially, you take the generic application, specialize it automatically, so the tool actually provides you that facility to then generate versions which are specific for, let's say, for an HTML with Java server pages or a WML delivery with Java server pages. And you can then look at this through simulators for the devices. You can look at how this part looks on different devices, and you can possibly go through a refinement step to essentially improve that. And the idea is essentially to maintain as much of commonality as possible across the different multiple devices, so that your application development and deployment effort does not go scale as n times a factor of n, but just a delta of or an epsilon of for each new device that you want to support. Right? We also in the tool provide if you already have an application which has been developed and which delivers HTML pages, we have in the tool this facility to take those HTML pages and so-called generalization, which is typically a very difficult thing to do in many cases. But again, we don't try to claim that we can do everything using this tool. All that the tool is essentially supposed to do is to provide you certain guidelines or a certain level of structure extraction from the HTML, so that you can then go in and go through this manual process, so that this process becomes a little easier to start with, rather than starting with raw HTML pages and mapping. Right? I have a demo of this tool on my machine, but so if anybody's interested later on after the talk, we can try to go through that. But that's overall just sort of the philosophy behind this tool. And in many cases, we find that that application development for multiple devices, you can really improve the overall development time using it as a tool like this. Yeah.
Is there a little bit more specifically about this kind of specialization? Because in the user interface RAM, just going from black and white to color is already a huge, or it requires a huge shift, and it goes just beyond just layout. You have to redesign your icons, and there's like
So the specific specialization steps that we are looking at is essentially both the layout on a single page of where the different pieces are laid out, as well as the split of a single page onto multiple pages. Right. So typically, when you take a WML application which is delivered, you have a deck of pages that are delivered. Which with a generic, sort of up and down keys that you can navigate through on these multiple pages, right? And one of the important things there is to decide where to break the pages. So the specialization tool first gives you a layout and page breaks for this device as recommended by the tool, and then you can go in there and change the layouts manually through the tool itself.
But when we go, if you look at forms, like some where you get some input, if it's just like display some page, and I can see that. But in many of those applications, you actually use them, especially in the commercial world, for getting information back from the device back into the server, and then it's the way you interact with it depends very much on how much real estate you have and your input. And so moving to a different device may actually completely change the design of those pages. It's not just choosing page breaks, it's like the interaction may require substantial changes.
Yes, we recognize this very well, right? And in fact, that's why I said at the beginning that the whole philosophy here is not to do everything automatically through the tool, right? So in many cases you have a class of devices, several of them, all Nokia 3 series phones may have little differences in the screen sizes and their and resolutions and whatnot, but you can lump them all together into one class, and you may be able to actually redesign your interface to just that one class and maintain it as that class representation for the output device. So that facility is there in the tool, for instance. If you ended up having to redesign the application significantly for a given device, you may very well end up doing that anyway. And what the tool does is it doesn't restrict you from from doing something like that. Right? So if it is necessary to actually redesign the application completely for a new device, you have the ability to do it, but there is support for maintaining the commonality among all of these versions. So for instance, it may end up that you have an application which has 15 pages that you want to display, and out of this, the richness in the input comes in only in 2 pages. And you may want to significantly redesign only those 2 pages. And what the tool allows you to do is that to keep the rest of the 13 pages common or generic in the application and just allow you to just redo those 2 pages. Right? So these are all the facilities that additionally you get with a tool like this, so that I don't end up having to then maintain a completely new version of the entire application. And when I make changes to the application, I don't have to end up changing the 15 different versions, but only change small bits of it. Right? That's the whole philosophy behind it. Yeah.
Actually, it's a comment to what Max asked. But was it the major promise behind the XML that one separates the structured content from the presentation? So you can handle this with the intelligent style sheet. So the device will have each device has its own way of representing the universal content on a screen, and content itself is highly structured and has no any page breaks or anything like that. It's just structured stuff. So and then the device has internal programming, let's say it's style sheet and XML, which really does all this adaptation. And as you said, it can actually skip 13 pages if these all 13 pages are marked as unimportant.
Yeah. There is a difference between, so in the design of XML or the philosophy behind it, so there is a separation of concerns, as you're saying, which is that you have a generic model for the data, and then you have ability through style sheets to change the user interface and the presentation of the information, right? This is all correct. Where it differs from reality is that it is still very expensive and very difficult to actually write the style sheets. And the style sheets tend to be not just device dependent, but also application dependent. So if you have an application which is being delivered, so you need to have a separate style sheet for each of the applications, and then each of the different devices, right? So the automatic transcoding or reformatting of the presentation to different devices, even though in principle it is possible to do, in practice it becomes very cumbersome to do, because again you are ending up with the same kind of scalability issues. So how many different versions of the application, the style sheets that you have to actually end up maintaining, right? So what the philosophy here is that you could plug in a tool approach like this still within an XML framework, and in fact you can see that internally, the structures that we are maintaining, generic structures are all XML based. The data model right now we're dealing with is Java Beans data model, not XML-based data models, essentially because that is the most widely deployed data model today, right? So you have to be able to maintain that, and legacy is something that we have to really worry about a lot, because 20% of the world's computers still run in COBOL. Okay, so anyway, so. In principle, it is true that this facilities exist, but you end up having to have facilities in a tool like this in order to support, even in the case of XML, ability to retarget applications or to present applications on different devices. Any other questions? Okay. I had one other section on security and privacy, but I think I will skip that for today. And thank you for patience with listening on a hungry stomach. you.